take a look at this check on heat and energy. So the first question, describe and diagram the transfer of energy between system and surroundings for endothermic and exothermic processes. So we first have to just make sure that we really do understand heat and temperature. So heat is the transfer of thermal energy, and temperature is the measure of molecular motion. And so we use those kind of interchangeably to understand more about what's going on with the system. But specifically, how is heat being transferred between an exothermic system and its surrounding, or between an endothermic system and its surrounding? So in an exothermic system, what we have is the system is giving off heat. So heat is going to travel, it's going to be generated by the system, and it's going to travel outside the system to the surroundings. The opposite is going to be the case in an endothermic system, and so we're going to transfer heat from the surroundings into the system. And that goes if we're looking at chemical systems or physical systems. So when this happens, we might want to know what the change in heat is. So delta H is the change in heat. We'll also use Q for heat, just depending upon which the application is. And I'll show you that in just a moment. So delta H is going to be the final heat. Okay, so H final minus H initial. And so when we do that for an exothermic situation, we end up with a negative delta H. Okay? And for an endothermic system, we end up with a positive delta H. And so that's going to be important for us to be able to evaluate what's going on with the energy of a system. So the first way that we're going to look at that is using something we call calorimetry. And so we're going to do some specific heat first. So in the second problem here on the check, it says how much heat does 250 grams of silver absorb when heated from 22 degrees Celsius to 68.5 degrees Celsius if the specific heat of silver is 0.235 joules per gram degree Celsius. And joules is that energy unit. And so we're going to use this equation. So Q equals C M delta T. And delta T is going to be T final minus T initial. So in this particular case, we are solving for Q. Q is the heat. Let me make that a little bit smaller here. So Q is going to be heat. How much heat? So that's going to be our Q value here. All right, so Q is equal to, and it gives us the specific heat. So specific heat is right here, and that is going to be what our C is. So that's going to be 0.235 joules per gram degree Celsius. We're going to multiply that times the mass, which was 250 grams. And we're also going to multiply that by the change in temperature. So you can either do change in temperature already, or you can do it at the end. So it is going from 68.5 degrees Celsius to 22 degrees Celsius. So order of operation, we actually need to do that change in temperature first. But when I calculate this, I'll actually show you how I do that. So I'm going to go ahead and get my change in temperature first. So 68.5 minus 22. I'm going to find out that number first. So that's going to be 46.5. Okay, I'm going to multiply that times the 250 for the mass. I'm also going to multiply that by the 0.235 for specific heat. And I find out that Q is going to be equal to 2,731. Now with Sig Figs, okay, so with Sig Figs, we started with 2 sig figs in this one. So our overall answer, even though the other ones are all to 3 sig figs, 2 sig figs is the least amount. So that's going to be 2,700. And then we need to know our units. And so when we go back and take a look at our units, it happens that grams is canceled by grams and degrees Celsius is canceled by degrees Celsius. So joules is our leftover unit, and so that's going to be in units of joules. Okay. So there is our answer to number 2. All right, and number 3, we are actually asked to find specific heat. So we want to find the C value. So we're still using the same equation. Q equals Cm delta T. Only now we want to find, we want to find the specific heat. And specific heat and heat are not the same. Heat is looking at the overall, what happens in the process, and specific heat is specific for that particular substance. So what is the specific heat of olive oil? If 435 joules of heat is added to 3.4 grams of olive oil at 21 degrees Celsius, and the temperature is raised to 85 degrees Celsius. So the actual heat of this whole process is 435 joules. That's going to be our Q value. Okay, so we want to solve for C. We can either rearrange our equation to solve for C, or we can plug in our numbers and then solve for our unknown. So let's plug our numbers in. So 435 joules is equal to C, and we're going to let C be represented by X. Okay, so C is going to be represented by X. And then our mass was 3.4 grams, and our change in temperature is 85 degrees Celsius minus 21 degrees Celsius. And like I said, you can go ahead and do that ahead of time. So if I do that, so we'll take 85 minus 21, that gives us 64. So we can actually go ahead and replace that with 64 degrees Celsius. Okay, so I want to solve for my X. So if you problem solve this way, we're going to go ahead and divide both sides by 3.4 grams and 64 degrees Celsius. And we'll do that on the other side. So 3.4 and 64, okay, those cancel on this side. So it turns out, when I go ahead and rearrange all this, X is equal to 435 joules divided by 3.4 grams. Actually, let's go ahead and make sure we do our order of operation written out kind of properly here, in 64 degrees Celsius. Okay, make sure if you're doing this all in one fell swoop in your calculator that you're putting those bottom values in parentheses. So let's go ahead and do that. I'm going to do 435 divided by, and then I'm going to start a parenthesis, 3.4 times 64. And my parenthesis, hit enter, and I end up with 1.999. Okay, so sig figs, we're going to end up with only 2 sig figs in our answer. So X, which is the specific heat, is going to be equal to, with sig figs, 2.0. Now we have joules per gram degrees Celsius. And that is our final answer.